Hi, my name is Gwen, and welcome to another episode of Scary Math. And today we're talking about the shape of the universe. So, have you ever trusted a map so completely that you walked right off a cliff? Ideally, not, right? But we built our entire understanding of reality on a mathematical map drawn over 2,000 years ago by a man named Euclid. But what if this map is wrong? And what if the straight lines you've been walking over your entire life are entirely circles? And therefore, let's take a look at the shape of the universe. So, Euclid gave us the rules of flat geometry, and the most famous is the parallel postulate. And it states that if you have a line and a path or a point outside that line, there's exactly one parallel line you can draw through that point. And this may feel obvious by creating tangents, but it feels like common sense. However, mathematics does not care about your common sense. Um, for centuries, mathematicians tried to prove the parallel postulate and failed. And why is this? This is because the universe is not flat. If you draw a triangle on the flat piece of paper, the angles add up to exactly 180 degrees. And that's the geometry that we were all taught in school and the geometry of a perfectly safe, flat world. However, now let's take a look at the sphere and Girard's theorem for spherical excess. Draw the exact same triangle over a surface of a sphere like the Earth, and the angles swell, they inflate, and the geometry itself bows outward, and the angles add up to more than 180 degrees. And so, with Girard's theorem for spherical axis, if you walk in a straight line on a sphere for long enough, you eventually come up behind yourself. And without this exact equation, every single GPS satellite in orbit would fail and global shipping logistics would collapse. And it literally steers thousands of commercial intercontinental flights every single day by proving that the shortest distance between 2 points is actually a curve. So let's talk about the saddle, the Gauss-Bonnet Theorem. So topologists use this profound equation to link the curvature of a surface directly to its fundamental shape. But it doesn't just describe geometry, it builds it. So material engineers, for example, they actively use this theorem today to design topological metamaterials, such as physical substances that can bend light around objects to create literal invisibility cloaks, or quantum computer chips that are physically immune to data corruption. So it gets a lot weirder. If the universe is curved like a saddle and what we call hyperbolic space, the angles of a triangle pinch inward. So they add up to less than 180 degrees. So in hyperbolic space, there are infinite parallel lines that you can draw through a single point, and it is a geometry of endless divergence. So let's look at Riemannian manifolds. Is actually kind of one of my personal favorite topics. And so this person called Bernhard Riemann realized that geometry wasn't just a flat grid we placed objects onto. The grid itself can bend, twist, and deform, and he created a mathematical language to describe spaces of infinite dimensions curving in on themselves. And so, in fact, he mapped the unimaginable. So Riemann gave us a mathematical tool that measures exactly how space is warped at every single point. So it's a brilliant abstract piece of pure mathematics, and essentially nobody thought it had any application in the real physical world until Albert Einstein. And so we're talking about the metric tensor, also known as the Riemannian metric tensor. And it's the mathematical engine behind the time dilation. And it calculates exactly how much faster time moves for a satellite in orbit compared to your smartphone on the ground. So without this tensor actively adjusting the clocks in space, For example, Google Maps would lose its pinpoint accuracy in a matter of minutes, and it's the absolute foundation of modern relativity. So, space-time. Einstein realized that Riemann's abstract math was the actual blueprint of reality. And so gravity is not a magnetic pulling force, and it's actually the literal bending of the non-Euclidean map. So massive objects warp the geometry of space-time around them. So let's look at matter and geometry and the geodesic equation. It's the absolute mathematical formulation of how objects move freely through curved space. And NASA actively uses this equation to slingshot probes around planets, stealing their orbital momentum to catapult spacecraft into the deepest, darkest reaches of the solar system, like the movie, right? So, as physicist John Wheeler famously put it, space-time grips mass, telling it how to move, and mass grips space-time, telling it how to curve. And they are locked in a cosmic dance. So when you drop an apple, Earth isn't pulling it down. The apple is simply moving in a perfectly straight line through curved space-time. So your perception of gravity is just the illusion of living in a non-Euclidean universe where you think things drop straight. They actually drop in a curve, and you are falling through warped geometry. So, what happens when you take Riemann's math to its absolute extreme? So, if you cram enough mass into a small enough space, the curvature becomes infinite and the mathematical map folds infinitely deep, also known as the black hole. So, if you take a look at the singularity now, you're talking about space-time that collapses into a black hole. This is described by the terrifying elegance of the universe's ultimate code, and these are what is known as the Einstein Field Equations. And they don't just describe reality; they allow us to hack it. They are the exact mathematical blueprints theoretical physicists use to design warp drives and stable wormholes, theoretically allowing us to tear holes in the fabric of space itself, again like movies. And they describe a point where gravity becomes absolute and all light is permanently extinguished. Einstein field equation. I mean, look how beautiful that is, right? So if you're taking a look now at the horizon, we're talking about something called the Schwarzschild radius, and it defines the exact mathematical boundary where the escape velocity of a collapsing star exceeds the speed of light. So it actually can bypass a little bit. It's terrifying, but this equation literally tells us how much we would need to physically crush the Earth down to the size of a marble to spontaneously detonate into a black hole. Yeah, at the center of the black hole, the metric tensor breaks, and the equations divide by zero. So mathematics literally ceases to function. So if you want to stop learning math, that's what you have to do. So the map of everything is destroyed, and whatever is at the center of that abyss is something we do not yet have the math to actually understand. So, thanks so much for watching. The next episode in this series is quantum entanglement, and we will explore what happens when the universe refuses to show its hand while being watched. See you there.